Welcome my dear students. This is my second video lecture on numerical problems from modern physics and quantum mechanics. In my first video lecture, I explained numericals on de Broglie matter wave concept and also Heisenberg uncertainty principle. Come, let us see few more problems from the same chapter. The remaining problems. Here is the next question. A measurement establishes the position of a proton with an accuracy of plus or minus 1 into 10 power minus 11 meter. Find the uncertainty in its position after 1 second. So we have to find the uncertainty after 1 second. Given data is very simple. Delta x, that is the uncertainty at present, and time taken are after how many seconds we have to find the uncertainty, that is after 1 second. Equation: delta v greater than or equal to h by 4 pi m into delta x. Substitute for h, m and delta x and calculate delta v. It comes out to be greater than or equal to 3.16 into 10 power 3 meter per second. So this is the uncertainty in the velocity. So with this velocity, let us see how much distance that proton would have traveled in 1 second. That is distance traveled. Delta x is equal to, that is distance traveled is equal to time taken into velocity, that is 1 into 3.16 into 10 power 3 meter, and the answer is 3.16 into 10 power 3 meter. So this is the minimum error in the position measurement after 1 second. So that's all about the question number 13. Next, how much time is needed to measure the kinetic energy of an electron whose speed is 10 meter per second with an accuracy of no more than 0.1%. So this is the error in the velocity. How far will it travel in this period of time? I repeat, how much time is needed to measure the kinetic energy? That means we have to find out t, whose speed is 10 meter per second, 10 meter per second with an uncertainty no more than 0.1%. How far will it travel during this period of time? Here, first I find out delta x. That means how far will it travel in this period of time? That means delta x I will calculate. That is h by 4 pi m into delta v. That comes out to be 5.79 into 10 power minus 3 meter. This is delta x. Now once I know delta x and once I know delta v, I calculate t. T is equal to delta x by v. Delta x is known, v is known, then it is 5.79 into 10 power minus 4 second. So v is 10 meter per second. Time taken is 5.79 into 10 power minus 4 seconds. So this is the time needed to measure the kinetic energy. See, remember, kinetic energy is not measured immediately. It takes so much of time for the measurement. This is the speciality of uncertainty principle. This type of uncertainty is not there when it comes to macroscopic objects. Energy, position, momentum, everything can be measured immediately and accurately. But that provision is not there in the case of subatomic particles. Next question. Repeat the same problem for an insect of mass 1 gram. See, here I have taken electron. Now I have to take the insect, which is also moving with a speed of 10 meter per second, but mass of the insect is 1 gram. And based on the calculations, you have to make the conclusion. So make conclusion on the result. It goes like this. Delta x once again. Delta x comes out to be very small. 5.26 into 10 power minus 33. Look at this. It is 10 power minus 3. This is 10 power minus 33. Compared to insect, the distance traveled by insect, the distance traveled by the electron is 10 power 30 times more. So can you make the difference between the two? Or in the other way, I can say, compared to electron, insect has traveled a distance which is 10 power minus 30 times less. That means insect has not literally traveled any distance. Okay. Therefore, there is no error in the measurement of the position of the insect. Time taken. Time taken is also very small. See, 10 power minus 34 second. Whereas here it is 10 power minus 4 second. Okay, just compare the 10 powers. The values of delta x and t in case of electron very much greater than that of insect. So based on this, we can conclude both distance traveled and time needed to measure the energy are too small to measure in the case of insect. Hence, we conclude that uncertainty principle becomes insignificant in the case of objects at macroscopic level. Okay, so that is the difference between macroscopic and microscopic states. Uncertainty principle is a major principle for microscopic, whereas in macroscopic there is no question of uncertainty at all. Next question. An unstable elementary particle has a rest mass of 549 MeV per c square. See, once again mass is given in terms of energy. And mean life 7 into 10 power minus 19 second. What is the percentage of uncertainty in the rest mass? So far we were calculating uncertainty in the position, momentum, energy and the time. This time it is uncertainty in the measurement of the mass itself. Okay, see, try to understand the concept of uncertainty principle and try to compare the same with microscopic and macroscopic world. In the macroscopic world, if you say mass of a pen is 100 gram, it is 100 gram only. You cannot say there is an error of 1% or 2%, or you cannot say most likely mass of the pen is 100 gram. That is macroscopic domain. But in microscopic domain, it is not so. It is impossible to measure even mass also accurately. This is what uncertainty principle is. No measurement is accurate. All the measurements are probabilistic. In fact, Einstein was totally against to the uncertainty principle. He did not believe the uncertainty principle. Anyway, let us continue this problem. Mass given, delta T given, convert the mass. I hope you know how to convert the mass. This step I already explained. 549 mega electron volt divided by c square. Okay, you get this. Then delta E, delta T greater than or equal to h by 4 pi, which implies delta E, I write it as mc square, then differentiate, then it becomes c square into delta m. C is constant, so you cannot differentiate, into delta T greater than or equal to h by 4 pi. Now you have delta m, rearrange the terms, substitute for h, c square, delta T and simplify, you get this answer. Once again, I have skipped all the substitution part. This part purposefully I am leaving it for you. You have to do the calculation and get this answer. Try to convince yourself. So that is the uncertainty in the measurement of the mass. When it comes to percentage of uncertainty, it is change in the value divided by original value into 100. So therefore it is 5.36 into 10 power minus 5%. Just for the sake of curiosity, do this problem for a particle of mass 10 kg. Okay, for a particle of mass 10 kg and convince yourself and see the difference between macroscopic and microscopic levels. Okay, the next question. An excited atom gives up its energy, excess energy, by emitting photon. The average time spent by it in the excited state is 10 nanosecond. Find the uncertainty in the frequency of the emitted photon. See, even in this problem also we have delta T and we have to find the delta nu, that is uncertainty principle only. So write the data, delta T given, delta nu required, and you have to start again with delta E, delta T greater than or equal to h by 4 pi formula only. So this is another way of expressing uncertainty principle. Delta E is the uncertainty in the energy, delta T is the uncertainty in the time. So it is also greater than or equal to h by 4 pi. So the product is greater than or equal to h by 4 pi. Next, in the place of E, write h nu and differentiate it. You get h into delta nu. h is constant, so you have delta nu as a differentiation part. Well, it is h delta nu delta t greater than or equal to h by 4 pi, and we want this delta nu. So proceed. Delta nu greater than or equal to 1 by 4 pi delta t, which is greater than or equal to 1 by 4 pi delta t, that is 10 nanosecond. Simplify, you get the answer, that is 8 into 10 power 6 hertz. This is the uncertainty in the frequency. Now comes the question on particle in one-dimensional box. An electron is trapped in one-dimensional potential box of width 0.1 nanometer. What is its energy in the first 3 allowed states? Here is the twist. That is not just first level, it is first 3 allowed levels. That means ground state, first excited state, second excited state. Totally 3 levels. Well, let us go ahead. Given width of the potential well, that is A, 0.1 nanometer. And the equation En equals n square h square by 8 ma square, where n is an integer, m is mass of the particle. In this case, particle is electron, therefore you have to take mass of the electron here. And A is given 0.1, h is Planck's constant. Now, for first allowed state, put n is equal to 1. That is called 0 point energy. This I have already explained in my regular class. E naught equals h square by 8 ma square. Substitute and simplify. While simplifying, please see that you get answer in electron volt. So you have to put 1.6 into 10 power minus 19 in the denominator. So E naught comes out to be 37.62 electron volt. Next calculation, that is for n is equal to 2, next allowed energy level. So here if you put n is equal to 2, then it becomes 4 times h square by 8 ma square. That is 4 into E naught. This whole thing is E naught. That is h square by 8 ma square is E naught. So we can write E1 is equal to 4 E naught. Similarly, E2 is equal to 9 E naught. E3 is equal to 16 E naught. And so on. So E1 equals 4 E naught, that is 4 into 37.62, that is 150.48 electron volt. So this is the energy correspond to first excited state. Coming to next level, that is n is equal to 3. As I told just now, E2 is equal to 9 E naught, that is 9 into 37.62, so much. So this is the first allowed level, this is the second level, this is the third level. Or in terms of ground state and excited state, we can say this is ground level, this is first excited level, this is a second excited level. Well, move on to the next question. Calculate de Broglie wavelength of electron in the first excited state if it is trapped in one-dimensional potential well of width 1 nanometer. So here width of the potential well is mentioned, and also in which state electron is present, that is also mentioned. We have to determine lambda de Broglie wavelength. So the data A is given, n is given. First excited state means n is equal to 2. Now recall suitable equations. This is from our previous discussions, that is from lambda, that is from de Broglie matter wave concept. Lambda equals h by root of 2 me and E equals n square h square by 8 ma square. So substitute for E in this equation. That means n square h square by 8 ma square you have to write here like this and do some simplification. H square cancel, m cancel, 2 1s are 2 4s are, and after doing small simplification, reshuffling the terms, we get it as 2a by n. I leave it to you, please do this simplification part. Then a is known, n is known, substitute. So lambda comes out to be 2 into 1 into 10 power minus 9 by 2, that is 1 nanometer. So remember, lambda is just 2a divided by n, where a is width, n is integer. For ground state, n is 1. For excited state, first state, n is 2. Second excited state, n is 3, and so on. So that's all about the question number 19. Next question. An electron is confined to a potential well of width 5 nanometer. Find its energy in the second allowed state, second excited state. Did you follow? Second allowed state, second excited state. Can you guess the number n value? Yes, you are correct. For second allowed state, n equals 2. Second excited state, n equals 3. So, n is decided, a is given. Let us find the value. En equals n square h square by 8ma square. Same equation. Substitute and simplify. Substitution part, as I told in my previous slides, I am skipping here just to see that you do the calculations on your own. See, remember, you have to substitute and do the calculations. At least that much you try on your own. It's going to be a good practice. Well, you get answer as 0.06 electron volt. Remember, here I have taken n is equal to 2. That is for second allowed state. Next, I should take n is equal to 3. When I take n equals 3, I get E2 as 0.135 electron volt. So, this is energy correspond to second allowed level. This is, that is n equal to 3, corresponds to second excited level. Well, let us proceed further. Here is a slightly different problem and also very lengthy problem. Read the question carefully. A particle is moving in one-dimensional potential well of infinite height and width of 25 angstrom. Assuming the particle is in ground state, find the probability density in an interval of 5 angstrom symmetrically about a by 2. Let me explain. As usual, particle in one-dimensional potential well is given and width of the well is 25 angstrom and infinite height. Height is infinite. And he says particle is in ground state. So, n is equal to 1. But what is your requirement? You need probability density. Where? From where to where? Over an interval of 5 angstrom. Symmetrically about a by 2. This particular part I will explain with the help of one diagram. See the diagram. This is potential well of infinite height. Okay. So, height is infinite. Width is finite. So, this way width is finite. Center of the well is here. This total width is 25 angstrom. Center is here. That is a by 2 position. So, this side it is 12.5. This side 12.5. Now, the question, from where to where we have to find the probability density. Is it from this edge to this edge? No. He says it is over an interval of 5 angstrom where symmetrically about a by 2. That means keep a by 2 reference and measure 5 angstrom width from here to here. So this side 50%, this side 50%. So from x1 to x2 it should be 5 angstrom. So length, the gap is x1 to x2, that length or the distance or the gap is 5 angstrom. It is marked symmetrically about a by 2. Just now I said this length is 12.5. In that this length itself is 2.5. Similarly this length is 12.5. In that this length is 2.5. So 2.5 plus 2.5, totally 5 angstrom. Now I must find out x1 and x2 value. Can you guess? Yes, you are correct. x1 is a by 2 minus 2.5. That means a by 2 minus 2.5. So this is x1. x2 is a by 2 plus 2.5. x2 is this much. Sorry, x2 is this much, a by 2 plus 2.5. So that is what I have written here. So x1 is a by 2 minus 2.5. that is 12.5 minus 2.5, that is 10 angstrom. This is A by 2 plus 2.5, that is 25 by 2 plus 2.5, that is 12.5 plus 2.5, that is 15. So x1 is 10, x2 is 15, so the gap is of width 5 angstrom. So we have to find the probability from here to here. It goes like this. Probability density formula: P equals integral of psi square dx between the limits x1 and x2. Psi is nothing but root 2 sine pi x by a. Psi square means 2 by a sine square n pi x by a into dx. Recall psi formula. It is available in the list of equations. It is nothing but normalized wave function. So psi square is 2 by a into so much, where n is an integer. Decide the value of n. Look at this part. He says it is in the ground state. Therefore n must be 1. So after substituting n equals 1 and taking this 2 by a outside, I get this form. So it is 2 by a integral of sine square pi x by a into dx. Let us simplify. You know, sine square theta is equal to 1 by 2 into 1 minus cos 2 theta. 1 by 2 into 1 minus cos 2 theta. In the place of theta, I have pi x by a. This is a well familiar equation and you might have already used this method in PUC. So I write this entire thing in this form: 2 by a, 1 by 2, 1 minus cos 2 pi x by a into dx. Here onwards it is simply PU level integration problem. Cancel 2 and then next step will be 1 by a into integral of dx, that is 1 into dx, minus 1 by a into integral of cos 2 theta, that is 2 pi x by a into dx. Proceed further. Integration of dx is x between the limits x1 and x2 minus 1 by a as it is. Integration of cos is sine of 2 pi x by a divided by 2 pi by a. But that 2 pi by a I have written here. So it becomes a by 2 pi. Please practice this problem. This is very important and at the same time very simple also. Well, cancel a and then next step becomes 1 by a into x2 minus x1. I have applied the limits. Even here also in the place of x I write x2. In the place of x I write x1. So I apply the limits. A is the width of the well. X2 upper limit, that is 15. X1 lower limit, that is 10. Well, substitute. Keep on simplifying. Purposefully I avoided angstrom here because this angstrom and this angstrom they cancel out. Okay. Therefore you need not have to write angstrom or you need not have to write 10 power minus 10 here. Even here also. Well, simplify. This first term becomes 0.2. You know how? 15 minus 10 is 5. 5 by 25 is 0.2. Minus of this whole thing comes out to be minus 0.1871. Again, my dear students, I leave this part for you to simplify. So, okay, substitute pi, that is 3.14 and simplify. Even here also substitute for 3 pi, simplify and convince yourself this answer you have to get. Well, P finally comes out to be 0.3871. That is probability density is 38.71%. So from x1 to x2 probability density is 38.71%. Well, I give you one small homework. Repeat the above problem for an interval of 5 angstrom symmetrically above a by 3. I give you clue. Come here. In the place of a by 2 write a by 3. Rest everything remains same. Here also a by 3 plus 2.5, simplify and all these steps will be same. In the place of x2 write your new x2 value. In the x1 write your new x1 value and go ahead and get this answer. Try to get this answer. Next question. A particle moving in one-dimensional box is described by a wave function psi, that is x root 3 for 0 less than x less than 1. So far I was taking this x as a, so this time he is taking it as x only. It is nothing but width. So I was taking it as a, now he is taking it as x. And psi equals 0 elsewhere, means outside psi is 0. Find the probability density between the interval 0 to half. See, this problem is very much similar to question number 21, but it is much simplified. You know how it is simplified? Psi is given, x1 and x2 values are also given. Lower limit, upper limit, both are mentioned. So just use this formula, probability density, substitute for psi, simplify, and then apply the limits x1 and x2. x1 is 0, x2 is half. In the place of x, substitute upper limit and lower limit and do small exercise. We get p equals 1 by 8. So probability density over an interval of 0 and half is 1 by 8. That's all about question number 23. Now I have come to the next question, again homework. A quantum particle confined to one-dimensional box of width a is in the first excited state. That means n is equal to 2. What is the probability density over an interval of a by 2 marked symmetrically at the center of the box? This is a very important question. It has appeared several times in VTU examination paper. Please do this problem on your own. Sufficient clue I have given in the previous problems. Based on that, try to solve this and try to get this answer. Well, dear students, with this I have come to an end of numericals from modern physics and quantum mechanics. I tried my level best to make the things as simple as possible. I hope this video helped you a lot. If you have any doubts, feel free, contact me either over phone or through email, and wait for my next session. Thank you very much.